One of my favorite speakers in the C++ world, Tony Vineyard, starts this brilliant talk by referencing another talk that he wants you to go watch after his talk is over. I'm starting this video the same way. You should go watch this Tony Vineyard talk after we're done here. It's wise, funny, and full of highly practical advice if you're in the business of writing good code. At one point in the talk, he says, write the functions you want to see in the world. He's telling sort of a parable about a junior engineer interacting with their mentor. Tony's delivery is unique and hilarious, but here's my paraphrase of it. The junior engineer, we'll call them June, asks their mentor, how do I read from the config file? The mentor says, there's a function for that. June says, what, like get config file? The mentor says, yeah, exactly. June says, well, what about the path for the config file? How do I get that? The mentor says, oh, well, there's a function for that too. June says, what is it? Get config file path? The mentor says, yes. June goes to compile their code and it doesn't work. Undeclared identifiers. June goes to the mentor and says, wait, these functions don't exist. The mentor says, I know. I guess you'll have to write them. I think this is poignant for a number of reasons. June had an intuition for functions that they wanted to exist, that sat at the right abstraction level, that were easy to piece together to solve their problem. Ever since I saw this talk, I've sat with this idea and reflected on what it is about these functions that feels so right. I want to quantify it and capture it. I want to write functions that feel this way. And I can't promise I've succeeded in cracking the code, so to speak, but here are my thoughts as of today. Without further ado, I present how to write the perfect function. So before we talk about how, we should talk about why. We should start by acknowledging that, much like programming languages themselves, functions are a purely artificial abstraction we have placed on top of computer hardware. Your CPU does not think in terms of functions. Your CPU executes streams of instructions, one after the next. Sometimes those instructions say to jump somewhere else and start executing those instructions instead. And that's it. Your programming language compiler is the one who looks at your function call in your programming language and translates it into the appropriate series of instructions intermixed with jumps. Don't take this for granted. We think of functions as fairly fundamental, but really they're a tool that your compiler has to go way out of its way to give you. I mean, if you think about it, we could just write our software directly how the hardware is going to execute it. That is, as a series of statements at the top level that have manual jumps that thread control flow appropriately. So let's take stock of why that idea typically doesn't make it off the whiteboard. Here are several reasons. One of my favorites is local reasoning, where if you design your function properly, you can think about how the code in your function behaves in isolation without having to think about the rest of your code at the same time. It's like your function creates a little sandbox that your code lives in that stops at the edges of your function, and changes you make outside the function do not affect what happens inside. This property is incredibly important as your system grows. It's extremely difficult to work with code where modifying this line over here tugs on an invisible string that breaks this line over here. Local reasoning is the ability to have confidence that the code you're looking at right now is all you need to understand what that code is doing. The other side of that coin would be abstraction. Now that our function is written and shielded from the outside world, we can also shield the outside world from it. Once it's written, we can mentally minimize it. We stick a name tag on its functionality, and from there we trust that it works, and we can use it like a little brick for building our larger system without having to zoom in and worry about its details. Now that our code is fully isolated, we can write automated tests for it. Because now we have a name tag for our functionality, we can invoke that functionality from multiple places. One place is probably going to be in our system itself, but we can also write code that runs separately from our main system, whose only purpose is to check that our function works properly. The more thoroughly we verify the function's behavior in our tests, the more sure we can be that it's going to work as expected in our real code where it counts. Even better, if we make sure to run these tests proactively and often, we can be sure that new changes we're making to our codebase aren't breaking this function. Notice that if we design our function to have local reasoning, we only have to rerun its tests if we change the function itself. But if our function isn't designed for local reasoning, we have to rerun its tests after any change we make anywhere in our codebase. It's interesting to imagine a unit testing framework that would skip rerunning tests for local reasoning functions that haven't changed since the last time the tests were run. This would be hard in general where most languages don't have a way to verify that your function supports local reasoning, but in a language like verse that has a special annotation for it, could be cool. Anyway, you might be yelling at the screen by now about code reuse. This is a reason people often give for why we should write functions. You'll hear things like, once you've repeated a piece of code n times, you should wrap it in a function so you can eliminate duplication. Sure, but what's n? Anecdotally, I think a lot of people you talk to might say 3. Once you've repeated a piece of code 3 times, that means it should be factored out into a function. Maybe. That seems like a lot of duplication to me. I mean, to get to 3, that means you already copy-pasted the code once to get to 2. Okay, so what if n is 2? That would mean as soon as you're tempted to copy-paste code once, it's time to pull it into a function. That's probably better than 3. But if you ask me, the right answer is 1. Once you've written some code in the first place, consider pulling it into a function. See the previous items on this list for why. It's not that code reuse isn't a nice feature of functions. I mean, it's the very thing that makes testability possible at all. But I think we should be proactive about pulling things into functions rather than waiting for code reuse to be a motivating reason. I'm sure there are other benefits of functions you'll remind me of in the comments, but let's go with this list for now. Notice again that these reasons on the left are distinct from these reasons on the right. Functions don't give your code fundamental power that it didn't have otherwise. They don't affect what code it is possible to write. An omnipotent, omniscient mind could write perfect go-to soup and accomplish all their goals no problem. But you and I, and your teammates, and even your AI agent are not like that. We are very limited in our ability to hold things in our heads and reason about complex systems. And functions give us the ability to break down complex systems into digestible pieces we have a chance at reasoning about. In other words, functions make programming easier. They're a tool for managing complexity. And we might consider what it would look like if we used this tool to its fullest potential. If we used functions perfectly, could we arrive here, where programming is easy? Maybe. I think certain things about programming are always going to be hard for us and anything that thinks like us. But for the rest of this video, I'm going to give some of my opinions on how we might design functions to try to approach this goal. I'm going to offer 3 overarching guidelines on what I think makes for good functions, with a bunch of examples mixed in along the way. As a framing device, we're going to pretend that we're working on a visual particle simulation with randomness and basic physics. This will motivate our first couple of examples we do. By the end of the video, you'll see that I kind of forgot to keep going with this idea, so the later examples won't be related as much. Anyway, for now, let's get started on implementing this particle system. So a lot of times when I have something I want to implement and I've made a plan for how it'll look when I'm done, but I'm having trouble getting started on the actual work, I'll start by sketching out some simple functions that I know I'm going to need. That helps the building blocks start to take shape and tends to give me a nice boost of momentum. But in order to start writing functions at all, we need to decide what kind of function we want to write. You'll often encounter sort of a taxonomy of functions that looks like this. First, there are pure functions. And these have some really nice properties, like determinism. If you pass in the same inputs, you'll always get the same outputs back out. That implies that you aren't reading from any mutable global state or anything like that. You also generally don't modify anything in pure functions. You don't modify your inputs in a way that's visible to the caller afterward, and you certainly don't modify any global state. There are a lot of functions in this category, like your math functions and your basic utility functions. But you can write your own non-trivial functions that follow these rules, and those count as pure functions too. What's the point? Well, pure functions give you local reasoning, which again means that you can fully understand what the function does just by looking at its body, without also having to think about other code that lives somewhere else. Pure functions are also testable, since you can count on them behaving predictably and not being sensitive to their surrounding environment. On the other side of the coin, we have impure functions. These functions are sensitive to their surrounding environment, and they might behave differently depending on the exact circumstances under which they're called. Mutation is also back on the table for these functions, and they can modify their arguments or even the whole state of the universe. These tend to be your more imperative functions that actually cause things to happen outside your program, like committing crimes or reading files or rendering something to your screen. And unlike pure functions, you cannot use local reasoning with these functions. You need to understand the larger world surrounding the function in order to predict exactly how it's going to behave and how it's going to go on to affect that larger world itself. For the same reason, these functions aren't very testable. It's often not practical to come up with isolated test scenarios that meaningfully verify the behavior of functions that are so sensitive to external state. So pure and impure is the dichotomy that you'll often hear. And I think this is useful, but in my genuinely humble opinion, I think this divide over-constrains pure functions. There are plenty of functions that we can test and do local reasoning about that might technically violate these rules. For example, what about a sort function that sorts its input in place? Well, this function's sort definitely does mutation on its input in a way that's visible to the caller, but it's most likely going to have the same result given the same input. And you can probably do local reasoning about the body because it's probably not thrashing global state in there. And you can definitely test it, throw something in and check if it's sorted when it comes out. As an example going the other direction, think of a function called getTime that reads from the system clock. This doesn't do any mutation and it doesn't really have any inputs, at least at the programming language level, but it's extremely sensitive to external state. It might kind of meet the criteria for being pure, but it's not very testable and its body doesn't have local reasoning. I mean, to predict what it's going to return, you have to look away from the code entirely to look at your watch. So for these reasons, for the rest of this video, I'm going to frame this taxonomy a different way. Instead of pure, I'm going to say that some functions are honest. They only access the outside world through their signature. In particular, they never read or write anything that isn't accessible through one of their function arguments. That means that the caller can fully control their behavior by tailoring their function arguments appropriately. This is going to cover a lot of our pure functions from before, but it also includes sort. Sort may modify some memory, but it only modifies the memory that you give it and explicitly give it permission to modify. Honest functions have the same benefits as pure functions. On the other hand, we have dishonest functions. I'm being a little cheeky here, but in some sense, these functions do lie to you. Their signature is not a complete representation of their inputs and outputs. And as a result, the caller cannot reason about them in a controlled way. This includes our impure functions from before, as well as getTime, since getTime reads from the state of the universe, which is nowhere indicated in its signature. Keep in mind that local reasoning and testability were two of the reasons we touted at the beginning as being reasons for writing a function at all. Dishonest functions still provide abstraction and code reuse, but otherwise they forfeit the other benefits of using functions by having a weaker contract. And these kinds of functions have an interesting property where they're infectious. If you have a dishonest function, all of its callers are also dishonest. An honest function cannot call a dishonest function, or else it becomes dishonest itself. That means that your legitimately honest functions, if they exist, are going to be at the leaves of your call tree, and your dishonest functions will be closer to the roots. We'll talk more about that soon. For now, let's pretend real quick that we're biologists in the world of functions, and we have these two classifications. Let's look at some examples of each and identify some specific species. I'm also looking forward to hearing about some of your favorite species in the comments. We'll start with the Honestus genus. This is a specimen we've already talked about. This is the true, pure function that takes some inputs and returns an output and doesn't modify anything. Yes, I'm glossing over the fact that this technically might modify the global heap by allocating string memory. I'm going to cheat and pretend that that's not an observable side effect. You got to draw the line somewhere. Anyway, this species comes in a couple of different breeds. Here's another specimen. This is a method now, but it still takes an input, an invisible this parameter, and returns a deterministic output without modifying anything. It's equivalent to this final specimen. There's another subspecies of the true pure function, which is the pure accessor. This type of function just creates a reference to some memory or sometimes a copy of some memory and returns it verbatim. So let's turn our attention to a slightly more exotic species. This function, vector clear, mutates its inputs, in this case an invisible this parameter. However, it's 100% honest and deterministic about the vector's state after that mutation. It's going to be empty, but still have its old capacity, if any. It doesn't return anything because it sort of returned the state that was written into the input. It's totally testable, and you can use local reasoning on the implementation. Beautiful specimen. We'll look at one more honest specimen, which is remove if, which is an algorithm you find in the C++ standard library. This specimen is going to mutate its inputs just like vector clear, but it's also going to return some information about what it did so that the caller can proceed accordingly, probably by doing the rest of the erase remove idiom. So this has two different output channels, if you will. It yields some output through mutation and the rest through a return value. Let's take a look at a couple of dishonest species now. I ran into this species once at a day job, and it's stuck with me ever since. I call this the dishonest accessor. It seems like it's going to be an honest accessor based on the name, but in reality, it is sensitive to global state. As you can see, it grabs all the assets we might need and then filters out the ones that are already loaded. The problem is this already loaded method reads from some global state and some asset manager system somewhere. That means that this function is incredibly sensitive to what has already happened elsewhere in the program at the moment that it's called. This made it very surprising for me when I came along and tried to use it and thought my code worked when I tested it, only to have it fail later on when someone else used it. That's because I was going off the name and was hoping to get a list of all assets that were required, whether they were loaded right now or not. But whoever originally wrote this function only needed the ones that weren't loaded, and so they baked in that assumption in a dishonest way. I have to say, I don't personally care much for this species. But I don't necessarily want you to come away hating every species in this genus. There are some beautiful specimens here. I mean, think about it. The pretty, type-safe, honest world of our programming language can really only extend to the bounds of our program. It can't go past that boundary. But the only way for our code to do anything interesting is to go past that boundary. At some point, we have to step outside our abstract machine and interact with the outside world, drawing something on screen, printing some output, writing a file, making a network request. Otherwise, our code is just spinning in an encapsulated bubble, not being useful to anyone. So calling a function like draw to screen might be the entire end goal of our program, in fact. So it's incredibly useful. But because our programming language can't reason about it, and because all dishonest functions are infectious, we need to have discipline in where and how we interact with them. In other words, this specimen is beautiful, but it has some teeth, and we need to train ourselves on interacting with it safely. We'll get to that in a second, but I want to prepare you first for one more genus we might encounter out in the wide world. A lot of times, if you're using a library or an application framework or something, you'll have a function like this. The framework says, hey, define this function called update, and I'll make sure it gets called every frame, or whatever the case may be. This does not fit neatly into honest or dishonest. It's sort of its own thing. I've named this genus Backwarda because where most functions abstract their implementation details from the call site, this function abstracts the call site from the implementation details. You probably don't know exactly where update gets called from within your framework. You just know that if you implement it, it'll get called at the right times without you having to worry about it. As a result, and we'll talk much more about this later on, I usually like to keep these function bodies as small as possible, jumping back into my own right side up functions as soon as I can. For me, this function only exists to glue my code to the framework code, and I want to keep that as its single responsibility. Here's another specimen of that type of function you may have heard of. The main function is a framework hook. You probably don't know exactly where or how main is called, just that it abstracts the entry and exit of your program in a way that will just work if you define it. Anyway, this concludes our biology excursion for now. Like I said, I'm looking forward to hearing about some beautiful or perhaps ugly species you've encountered in your fieldwork. But with this taxonomy in mind, we're finally ready for my first piece of advice for how to write the perfect function. So as we talked about, because dishonesty is infectious, you can only ever have honest functions toward the leaves of your call tree. But because honest functions have so many benefits, it's a good idea to maximize how many functions are honest versus dishonest. The way this ends up having to work is that you build your system, your business logic, out of honest functions, and then you inject dishonesty at the topmost possible level. We'll look at a toy example real quick, and then we'll look at a slightly more pertinent one relating to our particle system. So here I have a small program. I've color-coded which parts are honest versus dishonest. This program takes a string as input and prints as output every permutation of the characters in that input string. It does it using this next permutation algorithm, which is a real thing from the C++ standard library. And this call to sort is just set up for using that algorithm in this loop to do what we want. So you can see that we have honesty and dishonesty sort of intermingled here. And that makes it hard to work very effectively with this code. We can't write a unit test for the loop. All we can really do is run our program and type different stuff in at the command line and see if it works. So as a refactor, my suggestion is to push the honest parts down into their own function. This honest function just gets all the permutations, and then our main function does all the dishonest parts, calling into our function as needed. And the cool thing about that is now we can test our core logic by hooking it up to different dishonest stuff. Remember, the honest parts of your code are the core interior, and the dishonest parts are sort of the skin that connects your core logic to the outside world. With them separated, we can change details about that skin without having to mess with how to generate permutations. You can imagine another version of main that does file I/O instead of console I/O. I think you might agree that this is spiritually the same program we had before. Whether we're doing file I/O or console I/O is genuinely not an interesting or salient part of our program, and it shouldn't be tangled up with the parts that are interesting. Now, I do understand that after this refactor, we are allocating a vector that we weren't in the original version. And I think this is actually nice in principle. Our program is about finding all the permutations of an input string. So it makes sense that after running the core of our program, we are left with a list in memory of all the permutations. This is how this refactoring will look a lot of the time, where instead of executing some imperative dishonest function with your result immediately after you find it, you will build some data structure that represents the entirety of your result, and then some dishonest code can take that and process it after the fact. But I do acknowledge that this is more expensive, especially like for this example where the output really blows up as the input gets longer. This is going to cost big O of n factorial memory. So what you can do instead is use dependency injection. Here I've rebranded all permutations as for each permutation. The caller passes in a function object describing what they want to do with each permutation. Main here is printing out each one. This gets us back to exactly what we had in the first version, except our core logic is separated out and can be tested and otherwise repurposed. In fact, if we want to, we can implement all permutations in terms of for each permutation. So if your logic is concerned with visiting a bunch of values, I do suggest a for each style function at the bottom layer. Or in a language like Rust, you can implement a custom iterator that produces each value one after the other. For this kind of problem, it's a great way of getting great performance on top of great flexibility. Let's now look at a different kind of example, and this one will relate to our particles. So when we first set up our particle system, we need to sort of randomly scatter particles around before saying, okay, go and start animating. This might look something like this. I have a method on my particle world called populate. This is going to take as input a number of particles to create, and then it's going to generate that many particles. As part of doing that, I need to set up some random properties on each particle. I need to randomize its position and velocity and scale. To do that, I'm grabbing a global pseudorandom number generator and asking it for values. This is incredibly common, to have a global PRNG that you just conjure out of thin air when you need it. The way that PRNGs work is interesting. For a very basic mental model, you can think of them as being a box with some state in it. When we ask for a value, they use their internal state along with some algorithm to generate some random bits and form a suitable value out of them. At the same time, they mutate their internal state so that the next time you ask for a value, they generate different random bits. And this process is honest. It's deterministic what value you get based on the current state of the PRNG. And from any given state, it's deterministic what the next state is. We also get control over the initial state. You can seed the PRNG with an initial value, which is also deterministic. The same seed will always produce the same initial state. So this sounds incredibly deterministic so far. Where does the randomness come in? Well, the way to get the whole thing to be random is by getting the seed dishonestly. You'll commonly seed a PRNG using the current time, which is always changing, meaning every time you run your code, you'll end up using a different seed. As a good alternative, your operating system probably provides a way to get high-quality random bits to use for seeding. And notice that this whole design of PRNGs exactly abides by my advice to keep everything honest, but just throw in some dishonesty at the topmost level as needed. So what's the problem with this code? Well, we are reading from a mutable global variable in here. We're seeding the global generator and then using it within the function. The function itself does not have local reasoning because we have to look outside the function to know if the PRNG has been seeded appropriately. The fact that the PRNG is mutable also means that this code has subtle ties to every other piece of code that's using the global PRNG at the same time. What if someone else seeds the PRNG after we did, but before we got around to using it, or advances it from another thread, or from one of our callees, or just deletes our call to seed during a refactor? What if we want to test our particle world? What if our product team comes to us and says they actually want particle systems that can be perfectly reproducible so you can share the seed that you used with your friends? What if our product team doesn't care about that, but our QA team does because it would really help them test some odd behavior they're seeing? What if they suspect there's a bug in the particle's randomness and you need to debug that? It's happened in every code base I've ever worked on. The problem with doing any of these things easily or confidently is that we've baked our dishonesty into our particle world. This function is dishonest. Even this lambda is dishonest because we're reading and writing a global variable. Instead, we should be honest in our signature and say that in order to do what we need to do, we need a PRNG. Now our function is perfectly honest and has local reasoning. Its behavior is completely deterministic based on the state of the PRNG that we're given. At the call site, we can create a local PRNG and seed it with the current time. Now, this local PRNG is isolated from any of the scary action at a distance things we were worried about because we have our own copy, but it's still seeded in a way that will give us random results. But if we want reproducible results for any reason, we can just use a known seed instead, and as simple as that, our whole system will behave deterministically. We can test it and we can debug it. We can share cool looking particle seed values on social media or whatever. And if you're saying, wow, I genuinely don't care about any of these things from my particle world, fine. You can pass in the global generator to this function. It'll behave exactly as it did before. But you have all this flexibility if you change your mind later. But if you bake the global generator directly into the function, you can never get that flexibility back. That example was about honesty, but it dovetails fairly well into my next point, which is that your function signature gets used first and foremost by the human who is calling your function, and you should be nice to them. Think about what they're going to want and need, and think about how to use your signature to communicate effectively with them. I think we've all seen function calls like this, where it's very unclear what exactly is going on. This function signature was not designed in a way that's helpful to the caller. Any guesses what this last Boolean parameter does? It's also just cumbersome and error-prone to pass 6 arguments to a function, many of whose types can accidentally implicitly convert to other ones. A nice thing to do here is to create a struct that contains all the arguments and let the caller pass them in bulk. This can vastly improve the readability at the call site and can also help ease refactoring friction if you need to add or remove a parameter. Note that this is distinct from a separate anti-pattern, which is a function that requires you to pass in an entire struct or class when you really only need a couple things from it. This I do not like. This is like a cashier requiring you to hand them your entire wallet when they just need your card. It opens up dangerous possibilities, plus it excludes people who keep their cards in a rubber band instead of a wallet. This is different. This is a temporary struct whose purpose is specifically about marshalling data into this function. Another way to make this better without this struct is to use strong types for everything. I do like this approach quite a bit, although it often brings a lot of boilerplate with it. You also need to be cognizant of copying data in and out of these strong types. That also applies to the struct approach, by the way. Here's another function that is lacking in empathy. This function takes a vector of integers. That is a dynamically allocated, dynamically sized, contiguous sequence of integers. But I have an array of integers. It's on the stack, and I know how many there are at compile time. Why should I have to put my integers in this exact container you want? The standard library vector. I mean, maybe I'm using a third-party vector or a vector with a custom allocator. It's not fair for this function to dictate how I need to store my integers. And frankly, if it's just looping over them, it's none of its business how and where I've chosen to create and destroy them. This function would be vastly more empathetic and general if it used a parameter type like span, which sort of does type erasure over any contiguous sequence. Now I can call it with my integers living in any sort of array like storage. Now, I still can't call it with something like a set, which is not contiguous storage. Maybe the function needs it to be contiguous storage. Maybe it's calling memcopy in there or something. But if it's really just looping over the integers, the function should take it one step further and only ask me for something that can be iterated. It shouldn't ask me for stronger guarantees on its arguments than what it actually needs. But if it really does need strong guarantees, it shouldn't be shy about asking. We'll see that in this next one. Oftentimes you'll have 2 functions with a logical dependency between them. Must call A first. Now B has sort of a hidden input, which is it needs whatever A does to have happened. We can finagle a way to express this in the type system. A can return a value, maybe of an empty type, and then B takes it as a parameter. This type doesn't represent any real data, but is sort of a receipt proving that A has been called before calling B. As a concrete example of this situation, you might have B with a comment above it that warns callers that the mutex must be held before calling it. Well, we can do better, and in fact, we already have the hand stamp type that proves that the mutex is locked. Now, it's impossible to call B without locking the mutex. It also happens to prevent this common category of bugs where you accidentally forget to give the lock a name, and so it goes out of scope instantly, so the mutex is not locked when you call B. Now we have to give it a name because we need to pass it into B, so if we forgot to name it, we'll figure that out before our code will compile. It also lets us lock temporarily within the call expression if we want. So back to our particle system. Here I have a piece of code that might appear in an update function that runs every frame, where I update the particle's velocity based on its current acceleration. Pretty simple, but now I need to add some code that handles bouncing. So I'll call into the collision system and find what surface, if any, the particle should bounce off of this frame. But now, what's the math for figuring out the new velocity after the bounce? Well, I guess I don't know yet. Can't remember off the top of my head. And I'd rather complete my current thought in the code right here first before I go find the nearest math book. So I'll just make up a function that I wish existed and call it. This is like what June did at the beginning of this video. The function is probably going to need my current velocity and the surface to bounce off of, and I want it to return my new velocity after the bounce. I'll implement this later, but for now I get to finish what I was doing here without a major mental context switch. I'm basically using a function call to abstract some implementation details, not just spatially in code, but in time too. I don't know all the details yet, but I will later. Later has arrived. Let's dive in. How do we bounce? This white line will represent the surface we're bouncing off of. This ray is the velocity vector of our incoming particle. Our goal is to find the vector after the incoming ray bounces off the white line. In order to figure this out, we need the surface normal. In other words, a vector with a length of 1 that is perpendicular to our surface. If we take the dot product between our incoming ray and the surface normal, we can scale our surface normal by the result to get the projection of our incoming ray onto the normal. You can see this orange vector is like if the incoming ray were to cast a shadow onto the normal. Let's flip the orange vector around. Now to find the bounce, all we have to do is take our original vector and add one orange vector. This pushes us back up to ground level, and then add another orange vector, and this is now our bounce vector. Here's how this looks in code. I think. I double-checked this 1,000 times, but I never actually ran it, so I'm sure it's wrong somehow. But the part I want to focus on is this parameter, the normal. Remember how I said that this vector needs to have a length of 1? This math will not work if that's not the case. So how can we make sure that that is the case so that our function returns the right result? Well, one way would be to normalize the vector ourselves. Normalizing is when you take a vector and change its length to 1 while maintaining its direction. And this would work because normalization is idempotent, meaning it only has an effect the first time you do it. If we normalize a vector that someone passed us that's already normalized, that's fine. We just get the same vector back. So this would be one way to ensure that the normal is normalized, just do it ourselves. But it has a small but significant wrinkle, which is that normalization can fail. Here's how you normalize something. You just divide the vector by its length. But if the length is 0, you get a divide by 0 here. That, of course, causes problems. So suddenly we have an error case we need to handle. We can check if normalization is possible, but what do we do if it isn't? Well, a few things come to mind. First, we could just not handle the error at all and push the responsibility onto the caller, sentencing them to a lifetime of debugging infinities or nans in their simulation. That's not the most empathetic approach. We could at least assert our precondition for them, or we could return an optional, although checking for them pessimizes the happy path where they did the right thing. So I'm going to go out on a limb here and say that the problem is actually with the type of our parameter. We are telling the caller that they are allowed to pass in any vec3 at all, but really we require one with a very specific invariant. Uh-oh, I said invariant. Yeah, I don't think we want a vec3 here at all. We want a normalized vec3. What's a normalized vec3? Well, it's a razor-thin wrapper around a vec3 that, upon construction, establishes the invariant that the vec3 is normalized. It should be impossible to construct one that isn't normalized. On the other hand, you should make it easy to convert it back to a plain vec3. I seriously suggest making any conversions to vec3 implicit, or in C++, you can even consider inheriting from vec3. After all, a normalized vec3 is a vec3 in a Liskov substitution sense, and there should never be any correctness issue with implicitly upcasting to it. And now, armed with our normalized vector, we don't even need to worry about this question inside of our bounce function anymore. We know the vector is normalized. We push the responsibility for dealing with it to the caller, which is a better place for that responsibility anyway, because the caller is going to have more information about what types of vectors they are working with. Maybe there's a call site that can grab a normalized vector from a data structure that is already storing them in normalized form, or they can normalize once at the top of the function and reuse the result for multiple calculations. Or maybe they do need to find the normal vector themselves, maybe using this cross-product approach, but you know they're not going to forget to normalize it because they need their code to compile, and your contract is enforced in the type system. Back in my particle update, it turns out I don't need to pass the whole surface, just the normal. Luckily, my surface type already stores a normalized vec3 representing its normal. There's another benefit to using a separate type for normalized vectors, which is that we can specialize stuff based on that statically known invariant. For example, here's how we normalize a regular vector. Recall, we're essentially dividing the vector by its length after handling the failure possibility. But if we are asked to normalize a vector that is already normalized, we don't actually need to do anything. Normalization is idempotent after all. This might come up in generic code that works with vectors. If a generic function calls normalize on a generic input, and the caller happens to pass in a normalized vector, that call will magically collapse down to a no-op. Now what about this one? I mentioned cross-product a moment ago, which is another way of smushing two vectors together. Cross-product on arbitrary vectors just gives you back another vector, but if both input vectors have a length of 1, it turns out that the output vector will always also have a length of 1. So we could provide an overload that captures that fact in the type system. Should we? I don't know. Maybe. Returning a normalized vector would help the code that uses the result. That code could pass the result directly to our bounce vector function without having to pointlessly normalize the vector again. On the other hand, if we go too crazy with this, it feels like a slippery slope. It's not wise or feasible to encode every combination of pre- and post conditions in the type system like this, at least not in C++. So there's a line somewhere here that you don't want to cross, although I don't know exactly where it is. I feel like I just know it when I see it. Let me know what you think if you have a good idea of where this line is for you. We've spent a long time talking about function signatures, the outside of functions, and comparatively little time talking about how to write the inside. For that, there are a lot of great things we can learn from wise people who have come before us. There's the single responsibility principle, which comes from Uncle Bob Martin, who says that a class, or in this case, a function, should have only one reason to change. There's this one I really like from Tony Van Eerd, who says we should have separate functions for producing data versus acting on it. I guess now that I think about it, this is kind of similar to my split between honest and dishonest functions. And then there's this absolute classic from Sean Parent, who says that loops with non-trivial bodies should be pulled into their own functions, or better yet, should be expressed using generic algorithms. I'm horribly oversimplifying and underselling all these pieces of advice. I strongly urge you to look them up on your own. I'm going to leave links in the description, and you're going to need to click them. But I'm going to throw my hat into the ring here and give you my piece of advice, which I think arguably captures all three of these and maybe more. My golden rule is that every line of your function body should exist at the same level of abstraction. Your function is solving some problem. Imagine that problem being a structure made of bricks, like we talked about earlier. Writing your function should be about stacking those bricks, where the bricks are lower level functions that already exist. If you ever find yourself needing to conceptually zoom in on one of those bricks, fiddle with it a bit, and then zoom back out, that should involve a function call. It should not happen at the top level in the function. And if you shouldn't zoom into one brick within a single function, you certainly shouldn't zoom into more than one. That, to me, is what these three pieces of advice are saying. If you have a function that is mixing responsibilities, or doing too much, or using raw loops, you are probably failing to stack bricks and are instead bouncing between individual bricks within the same function. Let's look at an example. Here's a function that might live in like our game engine that powers our particle system. I'm really reaching here to try to tie this into the particle thing. We have some asset manager, which is some global registry of assets identified by a string name. Each asset has an asset type, and this function takes an asset name and a type and checks whether the asset with that name, if any, has a type that matches the passed-in type. I think I might have explained that badly, but you can pause the video and look at the function signature. Assuming the function is honest, you should be able to reason about what it does based on that. So let's approach this function like we're doing a code review. So what does it look like it's doing? Well, first off, it looks like we're resolving any case sensitivity issues by converting our asset name to lowercase. Apparently, this asset system uses case insensitive names. One pretty common way of accomplishing that is just always converting incoming strings to lowercase before looking at them. It works with uppercase too if you want. Now, this is a raw loop if I've ever seen one. We're supposed to be looking up some asset by name, but here we're way zoomed in on an individual brick, marching through our input string, fiddling with character codes one by one. We'll come back to this. The next thing we're going to do is a binary search. Apparently, we have our assets sitting in a random access container sorted by the name. If we don't find the asset, we do something kind of crazy. We actually just abort the entire application. That's probably not what we want to do, but we'll see. Then once we've found the asset, we check its type and return our answer. Okay, so what do we think? Well, I'm going to go back up here. This is really bothering me. Surely our standard library has a function for converting characters to lowercase. And I'm sure lots of us would reach for that in the first place instead of ever writing it out manually. We have an intuition that looking at character codes is too low level of an operation to belong in most functions. It should be wrapped up as a ready-to-use brick for building our higher level logic with. And if you do have that instinct, I want to take that and nurture it and use it to look at the rest of this code. So even with our two lower fixed, I'm going to argue that this function is still mixing levels of abstraction. One dead giveaway is that we have comments labeling the different sections of the function. What this usually means is that we're zooming in to part of the problem we're solving, then zooming back out, moving on, zooming into the next part, etc. And my golden rule is that you should never zoom in or out within a single function. So let's figure out all the levels of abstraction in this function by making a little outline of what it's doing. We'll start with the comments we already have. First, we're converting our name to lower, then binary searching for an asset with that name, then checking its type. Now we can flesh out each of these bullets a bit more. To convert our name to lower, we have to look at each character and then convert it to lower. For our binary search, we're doing at least two things. We're finding the lower bound, aka the place where the value should be if it's there, which involves a bunch of fiddly lower level stuff, almost like our string conversion did. And then we're checking if the item in that slot is a match. By the way, I double checked this binary search code so many times while making this slide, and now that I'm recording the voiceover, I can see there's a bug. That just goes to strengthen the point that this is not the kind of code you want spilling out all over the top level of your business logic. You want your binary search algorithm to be an encapsulated brick, well tested and optimized once, that you can use to build your solution to your problem without having to open the hood and write binary search every time. Anyway, lastly, we check the asset type. Not much to it. So on the right, we have 3 bullet points, but I actually want to split one more hair here. The first 2 bullet points are related, solving the same sub-problem, and the third is just using their output. So I'm going to group the first 2 together into sort of a sub-brick. The first thing we're doing is finding the asset. That entails converting the name and searching for it, etc. Then we use the result to check its type. So now that we have our problem outlined, we can figure out what should go in each one of our functions by grouping bullets that are at the same level of indentation. Our top level function is going to find the asset and check its type. We're also getting rid of that application exit thing and just returning a bool, but we could return some kind of richer result type to signal the difference between no, the asset had the wrong type versus no, the asset wasn't found. To find the asset, well, we first need our name to lower brick. We can do that in different ways. Here's one. However you do it, please be aware of different text encodings, and please note that the simplistic approach I'm showing here only works for ASCII strings. Anyway, now it's a one-liner to convert our string to lower. Great. Now we need our search. Now we just need to wrap our binary search in a function so we can call it. And now our find asset function looks lovely. It's super easy for me to believe this is correct, and that's because it's staying at the right level of abstraction. It says, here's the high-level series of steps you need to take to find an asset. And if you're interested in any specific one of those steps, go zoom in on that brick. Now, I went quickly over the binary search function. We wrote our own, and as I mentioned, there's a bug. An even better idea would be to use a binary search implementation that ships with your language or library. C++ has a very rich library of algorithms, and this one, lower bound, does exactly what we need. Now, we've added some gore back to our function, but that's okay. We're still staying at one level of abstraction, delegating to a lower level brick for what was previously a raw loop. I point that out to say that not every line of your function has to just be a single function call to another function. You can do stuff. We can call a binary search algorithm and check the result, but opening the hood of the binary search algorithm directly in this function is where I would draw the line. I do have one more bone to pick with this function, though. It's nice that finding the asset is all packaged up into one single brick, but we can reasonably assume that this function has invisible, delicate ties to other functions in this same class. For example, any function that adds a new asset is going to have to mirror the lowercasing of the asset name and the binary search for where to insert the new asset. Those sorts of invisible ties make it really difficult to change code in the future, like if we decide on a different way to do case insensitivity or decide we need to use a hash table instead of binary search. What we should recognize is that we are sort of maintaining an ad hoc data structure at the top level in our asset manager. And instead of managing that manually, we should recognize that and encapsulate that. Here, we're storing our assets in a case-insensitive map. It works however it works. Maybe it'll change how it works tomorrow. The asset manager doesn't need to know. This is now a brick that the asset manager can use throughout its implementation. By the way, for the past couple of years, I've been using this as sort of a template for how I name my maps. I don't know, it's kind of nice. It sort of nicely and succinctly describes what's in the map and how to look it up. Try it out if you like it, or let me know if you have a better one. Naming is hard. Anyway, the cool thing is that now that we have this data structure, which is like a super powered brick that can be used cleanly in lots of different scenarios, this function we wrote isn't really doing anything anymore. We can just interface with our data structure brick directly at the top level. And I don't know about you, but this is how I want all my code to look. I see this function and I have absolutely no doubt that it works correctly, assuming all of its bricks do. That's because its implementation stays at the same level of abstraction that my mind was at when I saw the function name and decided to see what was inside. It ends up reading like a high-level series of obvious steps, and all of its pieces will feel the same way if I decide to dive into them. So that's my golden rule for writing functions. Stay at one level of abstraction. By the way, it's incredibly hard to say that over and over near the end of the recording session. To wrap up, let's quickly summarize everything we've talked about today. We want to keep our systems honest so that we can reason about them locally and test them without being sensitive to the outside world. Then we want to inject that outside world stuff at the very top level. We want our functions to give their callers useful information about both their inputs and their outputs to maximize the chances of success on both ends of that relationship. We also don't want to over-constrain parameters for no reason. And finally, your function body should stay at one level of abstraction, and that will help it stay organized, easy to understand, and nimble in the face of change. I really appreciate you sticking around to the end. And I'm really encouraged to hear that there are so many people still so eager for this content based on the response to my last video. And yes, I'm recording this after reading the comments on that video. In that video, when I claimed that this video was already done, I might have been bluffing a tiny bit. I had yet to record the voiceover. But here we are. I'm so grateful to be part of a community that is as enthusiastic about this stuff as I am. And I hope we stick together for a long time. I'll see you all in the next one.